Hello! In this video, we are going to prove the following theorem. Let n be an integer greater than or equal to 0, and suppose f is a function from in to the real numbers, with a property that f of I plus 1 is greater than f of I, for all integers I, such that 1 is less than or equal to I is less than n. Then for all integers p and q in in, if p is greater than q, then f of p is greater than f of q. Now in this theorem, we are using the notation in, which represents the set of integers I between 1 and n. For example, I0 is the empty set, I1 consists only of 1, I2 consists only of 1 and 2, and so on. Now what this theorem is essentially saying is, if we're given a finite sequence of numbers with the property that starting from any point in the sequence, moving to the next point, we increase in value, then starting from any point in the sequence and moving to any later point in the sequence, we will also increase in value. Now also notice, we're saying n is an integer greater than or equal to 0. But this theorem is only interesting in the case where n is greater than or equal to 2, because in that case, this function will actually have an increasing nature associated with it. In the case where n is equal to 0 or 1, it turns out these two statements are vacuously true. Now, to prove this theorem, we're going to use induction on n. And so we're going to use induction on n to show for all integers n greater than or equal to 0, we have for all functions f from in to r, which have this property, then the function must have this property as well. So let's start with the base case. In the base case, we're trying to prove the theorem in the case where n is equal to 0. So we want to prove, given a function f from I0 to r, which has this property, well then the function has this property. So let's consider a function f from I0 to r, which has this property. From here, we want to show that the function has this property as well. In other words, we want to show for all elements p and q in I0, if p is greater than q, then f of p is greater than f of q. But remember, I0 is the empty set, so this is a statement about all elements of the empty set. Therefore, it must be vacuously true. So we have proven the theorem in the case where n is equal to 0. So this completes the base case. Now let's move on to the induction step. In the induction step, we consider an arbitrary integer n greater than or equal to 0, and we assume that the theorem is true for n. And from here, we want to show that the theorem is true for n plus 1. To do that, let's consider a function f from in plus 1 to r, with the property that f of I plus 1 is greater than f of I, for all integers I, such that 1 is less than or equal to I is less than n plus 1. And the whole goal is to show that our function f has this property as well. In other words, we want to show for all integers p and q in in plus 1, if p is greater than q, then f of p is greater than f of q. And to show that, we're going to be using the fact that we're assuming that the theorem is true for n. Now, to use the fact that the theorem is true for n, well, let's notice in is a subset of in plus 1. So if we consider the restriction of our function f to the domain in, well, let's call that restriction by the function g. Well, then by definition of the restriction of a function, we have that g is a function from in to r, and the output values of f and g are the same. So for all integers x in in, f of x is equal to g of x. Now, because we're assuming that the theorem is true for n, This means we can apply the theorem for any function from in to r that has this property. Now we know that g is a function from in to r, so all we want to do now is show that g has this property. So we want to show that g of I plus 1 is greater than g of I for all integers I such that 1 is less than or equal to I is less than n. And to do that, let's consider an arbitrary integer I such that 1 is less than or equal to I is less than n. Well then, 1 is less than or equal to I is less than n plus 1. So this shows 1 is less than or equal to I is less than n plus 1. But remember, our function f has this property. And it works for every integer that satisfies this inequality. So in particular, it must work for the integer I that we have here. So we can conclude that f of I plus 1 is greater than f of I. But since I satisfies the inequality 1 less than or equal to I is less than n, this implies we have 1 less than or equal to I less than or equal to n, and we also have 1 less than or equal to I plus 1 is less than or equal to n. These two inequalities are true because we're working with integers here. So this tells us I and I plus 1 both belong to in. So using the fact that g is a restriction, if we substitute x for I and substitute x for I plus 1, we get f of I is equal to g of I, and f of I plus 1 is equal to g of I plus 1. And so we can take this inequality, substitute f of I plus 1 for g of I plus 1, substitute f of I for g of I, so we have g of I plus 1 is greater than g of I. And so we have shown if I is any integer such that 1 is less than or equal to I is less than n, then g of I plus 1 is greater than g of I. And that tells us that our function g satisfies this property. So g is a function from in to r with this property. So since we're assuming the theorem is true for n, we can conclude for all integers p and q in in, if p is greater than q, then g of p is greater than g of q. But remember, we want to prove that the theorem is true for n plus 1. And at this point, we have considered a function f from in plus 1 to r with this property. And at this point, the whole goal has been to show for all integers p and q in in plus 1, if p is greater than q, then f of p is greater than f of q. So to prove that, let's consider two arbitrary elements, p and q, in in plus 1, such that p is greater than q. The whole goal is to show that f of p is greater than f of q. Now, since q is an element of in plus 1, we have that 1 is less than or equal to q is less than or equal to n plus 1. So in particular, 1 is less than or equal to q. And we know that q is less than p. And since p is an element of in plus 1, we have 1 is less than or equal to p is less than or equal to n plus 1. So in particular, p is less than or equal to n plus 1. Now we have two possibilities. Either p is less than n plus 1, or p is equal to n plus 1. And in either case, we're going to show that f of p is greater than f of q. Let's start with the case where p is less than n plus 1. Now, since we're working with integers here, we know that this implies p is less than or equal to n. So we have 1 is less than or equal to q is less than p is less than or equal to n. And so this tells us that p and q are both integers between 1 and n, so p and q are both elements of in. So p and q are elements of in such that p is greater than q. And based on what we've just proven about the function g, this allows us to conclude g of p is greater than g of q. But remember, by definition of the restriction of a function, we know that g of p is equal to f of p, and g of q is equal to f of q. So this shows f of p is greater than f of q. So this completes the case where p is less than n plus 1. Now let's consider the case where p is equal to n plus 1. And again, we want to show that f of p is greater than f of q. Now in this case, we have 1 is less than or equal to q is less than p is equal to n plus 1. So this shows that q is less than n plus 1, but since we're working with integers here, that implies q is less than or equal to n. And we know n is less than n plus 1. And this shows 1 is less than or equal to n is less than n plus 1. So we can use the property that the function f has. If we replace I with n, then we have f of n plus 1 is greater than f of n. And since n plus 1 is equal to p, f of n plus 1 is equal to f of p. Now the claim is f of n is greater than or equal to f of q, which is a reasonable claim because n is greater than or equal to q. And to see how that happens, well, we have two possibilities. Either n is equal to q or n is greater than q. Now, if n is equal to q, then clearly f of n is equal to f of q. So clearly, f of n is greater than or equal to f of q. So this completes the case n is equal to q. Now let's consider the case n is greater than q. If n is greater than q, well, this inequality tells us that both n and q are elements of In. And n and q are elements of In such that n is greater than q. So this tells us that we can apply the property that our function g has. Replacing p with n and replacing q with q, we have that g of n is greater than g of q. But by definition of the restriction of a function, g of n is equal to f of n, and g of q is equal to f of q. This shows f of n is greater than f of q, and thus f of n is greater than or equal to f of q. So in either case, whether we have n equal to q or n greater than q, we always have that f of n is greater than or equal to f of q. And so, going back to what we have here, we have f of p is equal to f of n plus 1, which is greater than f of n, which is greater than or equal to f of q. And this chain of inequalities tell us that f of p is strictly greater than f of q. And we're done. We see, in either case, whether we have p less than n plus 1 or p equal to n plus 1, we have that f of p is greater than f of q. So, putting this all together, we see, given any two integers, p and q in in plus 1, if p is greater than q, then f of p is greater than f of q. So, this proves that the theorem is true for n plus 1. And because we've proven the theorem for n plus 1, this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction, and so we have proven the theorem for all integers greater than or equal to 0. And so this completes the proof. And so yeah, that's pretty much it for this video.